Hello and welcome back to our discussion of the material in sections 10.5 and 10.6 of our calculus text. One thing I had failed to mention in the previous video on the ratio test is, or at least I failed to um, point out, is that in the reading that I've assigned for this section, example 4 gives an illustration of the types of series for which the ratio test isn't very, well, doesn't work at all. It's inconclusive because we get a value of rho of equal to 1. And the two examples that are given, and they're the canonical examples for this sort of thing, are p-series. P-series will not crack under the ratio test. They'll generally get a ratio of 1 from those. So I want to move on now and talk about the root test. It's also a test that is similar in nature in some sense, in terms of conclusions, for sure, to the ratio test. But there are specific instances where it's especially useful to use. And so, as before, we have summation n equals 1 to infinity. It may or may not start at 1, but we've got an infinite series. Our general term is a sub n. And we're going to let rho, this time, be the limit as n goes to infinity of the nth root of the absolute value of the general term. And the conclusions of the root test are exactly the same as those of the ratio test. If rho is less than 1, the series converges. If rho is bigger than 1, the series diverges. And I should have said converges absolutely up here. And 3, if rho is equal to 1, the test is inconclusive. The root test is particularly useful when our general term is a power, and particularly an nth power, because we're taking the nth root. And so we're going to be able to multiply exponents, and things will simplify pretty nicely for us, generally speaking. And that's what we've got in the example that we're working with here. Summation n equals 1 to infinity of the quantity 2 plus 1 over n to the minus nth power. And so our general term is that expression that I just read, 2 plus 1 over n, all to the minus nth power. So rho is going to be the limit as n goes to infinity of, I'll write the absolute value. That's redundant in this case because the expression inside is always positive, but the absolute value of 2 plus 1 over n to the minus nth power, all raised to the 1 over nth power. Again, the whole point of using the root test is oftentimes to work in situations where I can multiply these exponents and simplify things really nicely. So here I've got something raised to the minus nth power, subsequently raised to the 1 over nth power. And so I'm going to get the limit as n goes to infinity of 2 plus 1 over n to the minus 1 when I multiply those exponents together. And, well, let me remind myself that that's the same as the limit as n goes to infinity of 1 over 2 plus 1 over n. As n gets big, this goes to 0, and so my limit is 1/2, which is less than 1. So by the root test, summation n equals 1 to infinity 2 plus 1 over n to the minus nth converges absolutely. So there's one problem involving the root test on our homework assignment. It gets a lot less use overall than the ratio test, but we want to at least be able to deal with it in the obvious cases. But the ratio test is going to be a much, much bigger player for us coming up in these next examples as well, because I'm turning my attention now to some material out of section 10.6. I'm breaking this up into two parts in the homework. And so we'll, in the homework that's on WebAssign, and so I'm breaking it up into two parts in my video series as well. So at the beginning of section 10.6, we're introduced to the notion of a power series. And in some sense, we can think about this as an infinite degree polynomial. So a power series in the variable x centered at x equals a is of the form summation n equals, and we'll start this one at 0, summation n equals 0 to infinity c sub n x minus a to the n. And so if I were to write out the first few terms, you begin to see why we might call this a polynomial, an infinite degree polynomial. C0 plus C1 x minus a plus C2 x minus a quantity squared plus C3 x minus a quantity cubed plus dot dot dot. And so the question, the big question we want to ask usually for this, or often we want to ask for this, is what values of x make the series converge? So as I said, that we've got, basically this is we can think about this as a function, an infinite degree polynomial, and so we can plug in values of x, and we want to know, well, what numbers can I stick in for x that will give me a series that converges to a finite number. And so we have an important definition here. The interval convergence for a power series is going to be the set of numbers for which the series converges. So when I substitute those values in for x, I will actually get an infinite series. And so our first set of problems with respect to power series are to find the interval of convergence for the power series. And as you see what I've got, as I've written here, we are generally going to be using the ratio test to help us find the interval of convergence. But because the ratio test is inconclusive when the ratio is equal to 1, then that means we're going to have to do other things to test to see if the power series converges at the endpoints of the intervals that we're going to find. So I've got a few examples here I want to try to work, and we're going to get a good workout with the ratio test as well. So our first example is summation n equals 1 to infinity x to the n over the quantity n times 2 to the n. So I'm going to be writing out here my general terms. And so if I'm applying the ratio test, I'm going to write out a sub n and a sub n plus 1. So a sub n is x to the n over n times 2 to the n, and a sub n plus 1 is equal to x to the n plus 1 over n plus 1 times 2 to the n plus 1. So I'm going to let rho be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And absolute value is going to play a big role here because our variable x could take on negative or positive values, and so we're going to need to include or keep absolute value around. So I'm going to do what I was doing before, though, when I was working with the ratio test. I'm going to go ahead and write this product, this quotient of quotients as a product of quotients by flipping the denominator and writing it as a product. And so what I'm going to get is I'm going to get x to the absolute value of x to the n plus 1 over n plus 1 times 2 to the n plus 1 times n times 2 to the n over x to the n. Now already I can see a little bit of cancellation here. I'll take my time in this example and write it out a little bit more clearly. And I've made a mistake, so let me try to fix that here. This is x times to the n over n plus 1 times 2 to the n times n times 2 to the n over x to the n. And so I can see there's a lot of cancellation here with those terms. And so what I'm going to get, when all is said and done, is the limit as n goes to infinity of the absolute value of x times n over the quantity 2 times n plus 1. Now, n is necessarily positive here, so anything involving the absolute value of n can just be written as n. So that's why I don't have absolute values around anything but the x at this point. So let me go ahead and then rewrite it this way. Limit as n goes to infinity of absolute value of x times n over n plus 2. The absolute value of x doesn't involve n in any way, so I'm just going to be focusing on this part. The degrees of both numerator and denominator are 1, so the limit as n goes to infinity is going to be 1/2 in this case, and so my limit value of rho in this case is 1/2 times the absolute value of x. And we know then that the series converges when 1/2 of absolute value of x is less than 1. Well, I can multiply that both sides of that inequality by the positive number 2, and then I can rewrite it. I find it pretty helpful to rewrite it without absolute value. The absolute value of x is less than 2 when x is between -2 and 2. So I know the series converges at least on the interval -2 to 2. But the test is inconclusive at the endpoints of the interval, and that's because I would get a value of rho equal to 1 when x is equal to 2 or -2. And so I have to test those separately. And I test them by plugging them into the original series. So I'm going to plug them into the power series. So I'll do -2 first. When x is -2, I get summation n equals 1 to infinity, -2 to the n over n times 2 to the n. Right? So I'm just plugging in -2 right up here. And I want to simplify this. So -2 to the n can be thought of as -1 to the n times 2 to the n. And now my 2 to the n's cancel. And so we've got an alternating series. And we want to go back and remember how we test alternating series. I look at the ratio, I look at the limit as n goes to infinity of the general term without the -1 to the n. So I take the positive term part of that and look at the limit as n goes to infinity of that. Well, in this case, that's equal to 0. So this converges by the alternating series test. So -2 is in the interval convergence. What about x equals 2? Well, I get 2 to the n over n times 2 to the n. The 2 to the n's cancel. And so I get summation n equals 1 to infinity 1 over n. This is a divergent geometric series. Divergent p series. It's the harmonic series when p is equal to 1. So it converges at -2, it diverges at 2, so the interval of convergence is the closed half closed, half interval, half closed, half open interval, minus 2 to 2.